Let me just sketch out what's going on here. We're told that a polygon has n vertices where n is greater or equal to 3, the following properties. Every vertex of the polygon lies on the circumference of the circle, called an inscribed polygon, but the center of the circle must lie inside the polygon. So I couldn't, for example, draw a triangle like that. Let me draw a five-sided shape. The radii from the center then form n triangles. So in my case, for this example, 5 triangles. And they've got equal area. So actually, the one I've drawn here is not valid because they don't look like they have equal area. Like this one looks a little bit bigger than this one, but it's just a sketch to get an idea of what's going on. Now we're asked to show for which values of n are these properties sufficient, though implies that the polygon must be regular. Well, all these sides are the same length, they all are. So the area of any given triangle is going to be a half r squared sine theta. That's a half AB sine C. So the only way they're going to have equal area is if sine theta is the same for every triangle. So of course, if the angles were all identical, we would get sine theta being the same and hence a regular polygon. What this question is really getting into is it possible to choose, have unequal angles that give you the same value of sine theta that then lead to the same area of your triangles, but not a regular polygon? Let's take a look into it. I'm going to stick with 5 for the moment. So if I've got my 5-sided shape, then what about, okay, because here's the thing, sine theta is the same as sine 180 minus theta. Because if you look at the sine graph, we're getting into territory, this is called the ambiguous case of the sine rule. You can get more than one solution when you have an SSA triangle. If you have two sides and an angle, then you could potentially get more than one triangle because of this graph here. Two different values of the angle give me the same value of sine. So why don't I just pick my pentagon and say, you know what, I'm going to say that these 4 are all going to have the same angle, theta. And can I construct this one so it's 118 minus theta? Because if I can make such a construction, then what I will have done is have, I'd meet all of the conditions. The vertices are lying on the circle. So the sides are R and R on all of them. The center's inside, no problem with that, because what that means is that, yeah, as I go around that point in the middle, they're all going to add up to 360, and the areas are equal. So what I can say now is that 4 theta plus 180 minus theta must equal 360. This is going to be possible. That means 3 theta is going to equal 180 and theta is 60. So it looks like we can do this. We can have 4 60-degree angles and then a 120-degree angle. And that will give us 5 triangles with an equal area. But in the case then of 5, it's not sufficient to deduce the polygon is regular. And I've drawn this a little bit earlier. This is such a polygon. Okay, it's made up of 60, 60, 60, 60. This is 120. They do have equal areas. It might not quite look like it, but actually if I kind of split this into 2 and like moved it here, it is the same. So yeah, basically it is not sufficient for n equals 5. I just happened to pick n equals 5 to start with, but now let's look into some more. Before I generalize, I'm going to look at a few other cases. Let's take a look at n equals 4. So here, if I made 3 of the triangles have the same angle, and then the 4th one have 180 minus theta, this would equal 360. which would mean that 2 theta equals 180 and theta equals 90. But actually, that ends up meaning they all have the same angle. Okay, that did not work. But what if instead I say that two of them have angle theta and two of them have angle 180 minus theta? Okay, maybe this will work. So then 2 theta plus 360 minus 2 theta equals 360. And actually, this is always true for any value of theta. So what we're saying here is that we could draw a circle. We could draw maybe a line going there to there, and then have a triangle going down. So I have a line going down connected to the center here. Okay, and these triangles would all have the same area because if that one is theta, that would be 180 minus theta, and a half r squared sine theta is the same as a half r squared 180 minus theta. Same area, but this is clearly not a square. This is a rectangle. And theta could be anything. So I could pick, say, 30 here, and this is 150. Okay, so that actually, although it didn't work with one of them, it worked with two of them. So it's not sufficient for 5 or 4. Definitely, let's take a look at 3 now. So in this scenario, I can't have them all having the same angle because then it would be, I'm trying to work out that trying to create a construction where it's not regular basically. So I would have 2 theta plus 180 minus theta equal to 360. Two of them have the same angle, one of them different, but then theta would end up being 180. And we wouldn't actually get a triangle out of this. We draw this, we would just draw a straight line going across. Two of the angles are 180 and one of them is 0, not a triangle, which actually means this is not possible. And in fact, the only possibility is that we can get a regular polygon. In this case, three of them would be the same. 3 theta would equal 360 and theta would be 120. We could do that. So that's 90, looks about 120. So what I'm saying is actually it is sufficient when n is equal to 3 because we saw what happened when we tried to have two triangles with one angle and then a different one with a different angle that was 180 minus the other angle to get the same area. Actually, it just fell apart because theta ended up being 180. Sufficient for n equals 3. So we just haven't, we've shown that it's sufficient for n equals 3, not for 5 or 4. We've not yet shown that it's not sufficient or if it is sufficient for n greater than 5. We're going to have to look into that. But there's an infinite number, of course. N, let's just say n greater than 5. It's not going to, we could include 4 and 5 in this maybe, I'm not sure, but n greater than 5. So let's try and make it so n minus one of the angles have that same angle theta. And then there's going to be one, which is 180 minus theta. This is back to my pentagon setup, which did work. So it seems like good motivation to try. It didn't work for the 4, but let's see if it works here. So that would equal 360. And then I would get, well, n minus 1 theta minus theta is actually n minus 2 theta, and that's going to equal 180. So then theta would equal 180 over n minus 2. And this means that, yeah, we're going to get our value of theta all the same, and then we're going to get 180 minus theta that's different. The only time it would be the same is when n is 4, because then we get 90. But if n was, say, 6, you do 180 divided by 4. And there's no way when you do 180 minus that, you get the same angle again. So what I've actually shown is it's not sufficient. We are not necessarily going to get a regular polygon when n is greater than 5. I just want to say this one more time. I've just generalized my method from before. I've said that, right, I've got a circle. I'm going to try and create all these triangles that are like the same. And then I'm going to do one that's like 180 minus, just like I constructed with my pentagon. And if I can construct such a shape, then it does not guarantee, well, the polygon wouldn't be regular. So it's not sufficient. Back to the original question, it's not sufficient to deduce the polygon's regular because you could construct one that's irregular. So I said that n minus 1 of the n angles are going to be theta, and the other one's going to be 180 minus theta. They must still add together because they meet at the very center. They must add together to give 360. I've just rearranged it to give me theta is 180 over n minus 2, and that gives me a construction for how I can make such a polygon where this is true. We've already dealt with n equals 3, 4, 5, but if n is 6 or whatever, we're going to get a value of theta that's definitely different than 180 minus theta, which means I can construct such a thing for all of these values n greater than 5, which means it's not sufficient for 5 or 4 or n greater than 5. And we're there. Okay, it's a bit messy, but we're there. The only value where it is sufficient is n equals 3. Okay, it's quite a tough question to explain. Tough question in general, but well done on your efforts on it. It's really good, I think. Good question. Thanks for watching. Center, they must add together to give 360. I've just rearranged it to give me theta is 180 over n minus 2, and that gives me a construction for how I can make such a polygon where this is true. We've already dealt with n equals 3, 4, 5, but if n is 6 or whatever, we're going to get a value of theta that's definitely different than 180 minus theta, which means I can construct such a thing for all of these values n greater than 5, which means it's not sufficient for 5 or 4 or n greater than 5. And we're there. Okay, it's a bit messy, but we're there. The only value where it is sufficient is n equals 3. Okay, it's quite a tough question to explain. Tough question in general, but well done on your efforts on it. It's really good, I think. Good question. Thanks for watching.